All right, so we're ready to start back. So I'll introduce Professor Eric Chittumbar. So Professor Chittumbar, this is his second year now at Illinois, and so he's an expert in quantum information. So we have him teaching about signals, which is unrelated to quantum.
Thank you very much, Linford. It's awesome to be here and talking to you all. Actually, one can make an argument that there is a connection between quantum information and signal processing. In fact, one of the things we're talking about today is something known as a Fourier transform. In fact, there's a quantum version of that, and it plays an important role in quantum algorithms. But we won't. Okay, not going to get into that. What we are going to talk about is signal processing, and we're just going to get a sense of some of the concepts that are involved in signal processing. And so the presentation here is taken pretty much out of chapter 10 of your book. So I hope you guys will be able to follow along. And the way that we'll do this is I'm just going to give you some ideas, some concepts, just the general broad brush of what signal processing entails. And then there's going to be some demos that we'll do in between, some kind of hands-on things where you can get a sense of these concepts. All right, so first, just the basic ideas. So what is a signal? I mean, this is something that we're all intuitively very familiar with. But if we wanted to write down a definition, a signal is some time-varying or spatial-varying set of data. And if you think about like an example of a signal, if I have a flashlight and maybe I'm shining it at you, and maybe we're using Morse code or something, that would be one example of a signal. But in general, it could be anything that we can represent with a function f, and it depends on t. Right? So this would be a time-dependent function, and f is like the amount of signal that you have at a given moment in time. All right? But you could also have a spatial varying signal, which would look something like this, where now you have 3 coordinates x, y, and z, and then this would give you the amount of signal at any point in space. Right? Yeah?
Example, that might be what they do when they stand out on the boat and have the flags, and they do the various signaling.
Yes.
That has everyone is a letter, and you can spell things out.
Yeah, exactly. That would be.
Because there, the position of the hands are at least x, y, if not.
Yeah, actually, that could be a little bit of both, right? Because there's a time ordering of it as well, right? And so you need to understand the positioning also in the order of it as well. So that's a mixture of both the spatial and time varying. Yes. Yeah, exactly. Another example of just this would be if you were trying to look at if you had some sort of map, and f would be maybe the elevation at a given point in space, right? So that would be a way that you could represent. That would be a type of signal. It would be like the elevation signal. Or you could have color as well. So if you look at a picture, x and y would be like the coordinates on the picture, and then f could be maybe the frequency of the color being reflected. So those are just examples of signals. But the first take-home message is that we deal with signals ubiquitously. Everywhere we go, we have some sort of signal that we can represent in this manner.
Is a CD-ROM the information on it considered a signal?
Right. So the information itself, when the way that it's read onto your computer, that's using signals. So basically, there's a light that gets shine on the CD, and it has a particular diffraction pattern, and that diffraction pattern is a signal that's then sending information to your optical drive head.
Information is stored on the CD.
Yes.
X, Y coordinates, and then
It's read.
dimple or flat, right?
Yep. Exactly. Okay, so we can characterize signals in 2 different ways of either being periodic or aperiodic. And here's the first one on the left is like an aperiodic signal. And this is sort of intuitive. What this means is that periodic means that you start at one point and you come back to the same waveform at another point along the x-axis. Right, so here the way that this just peaks here and then it drops off, decays, till t goes to infinity on both directions. So there's really no repetition here, right? It has this one peak and that's it. Mm-hmm. Whereas on the one on the right, there's repetition. You see that I go up, down, up, and then I repeat the same behavior. Okay. So this idea of a periodic function is crucial in understanding signal processing. But intuitively, it's very simple. It's just something that repeats itself. And so why is this repetition important for signals? Because it reminds us of something that we learned in geometry class. Okay? So we're not going to get too deep in the math here, but it's important just to understand a few concepts. And I'm sure at some point all of you guys, if maybe you're teaching this in class, if you're teaching trig or something where you're drawing out sine and cosine functions, right, like this. Okay, so this is a periodic function, and here's the basic components to a sinusoidal function. You have a, which is the amplitude, right, and the amplitude tells you basically how high your wave is going and how low it's going. Right? So in this example, your amplitude is 1. Why? Because the peak goes up to 1 and it goes down to -1. Okay? So that's A amplitude. That's fairly intuitive to understand. So inside this parentheses here, this is basically telling you how the shape behaves as you move along the x-axis. So this omega here, which looks kind of like a W, this is called the frequency. Okay, and what the frequency tells you, this is a really important quantity. This is telling you how many repetitions you're making or how many cycles you're making per second. Okay, so if you look here, so here's t. So we start here, I guess if this is like at roughly -6. Okay, and then it gets back here 6, right? So in total, it took about 12 seconds to make one cycle. Right? Yep. Okay. So that would give then 1 over 12. So in one cycle per 12 seconds would be the frequency. All right, and then there's this other quantity here. This is phi. This is known as your phase. Okay, and the way to think about what this phase is doing is it's going to take this waveform, it's going to shift it left and right on the t-axis. So here, this is a picture taken from the book, which shows two sinusoidal waves which have the same amplitude and same frequency, but they have a different phase. And you see then all that the phase does is it just takes it and shifts it by this amount theta. Okay, I remember when learning about these, and it's something I don't know what grade it was I learned about it, but everything kind of just makes sense because you get a nice satisfactory feeling of drawing this out and seeing, okay, A goes up like this, and you can actually measure the frequency, and you can look at the phase shift all just by looking at the graph. So this is a really nice connection between the algebraic expression of your sine function and then the graphical depiction of it. Okay. So, and these are what I say here, these are the building blocks because really this is how we're going to understand periodic functions in terms of these sinusoidal functions, general periodic functions. Okay, so let's take a quick break and let's do this activity. So this is pulled right from your book.
Okay, so we're going to do this activity as a group. So there are 3 different waves, and you'll notice they have amplitude and frequency information. So let's first talk about this blue wave in the middle. What's its amplitude?
10.
10, okay. And then what's the frequency?
Pi.
Okay, so pi is what's known as the period. So the period tells you how long it takes to repeat, and it's related to frequency. And I should say that there's linear frequency and there's angular frequency. So linear frequency is 1 over the period. So the linear frequency is 1 over pi. But then there's angular frequency, which talks about the number of cycles. So angular frequency is omega 0. It's the number of cycles per 2 pi. So in this case, the angular frequency, the number of cycles per 2 pi is how much?
2.
2. Okay, so the angular frequency omega 0 is 2. So in this case, we have amplitude of 10 and frequency of 2. So this is 10 cosine of 2t. So now let's look at the green one. So the green one has, so this is F2. The green one has amplitude of, what's the amplitude of the green one?
5.
5. And what's the angular frequency omega 0?
2.
2. So this would be 5 cosine of 2t. And the reason it's cosine is because it has a maximum at 0. And so cosine starts off at 0, or sorry, it starts off with its maximum at 0, and then it starts to decrease and then oscillate. Whereas sine would start off at the origin and it would go up to its maximum and then down. Okay, so now let's look at this wave. The amplitude of this wave is 5. And what's the angular frequency?
3.
3. So this would be written as 5 cosine of 3t. So I'm going to jump and do another example. First wave, I'll ask people to tell me what this entire function is. So say the amplitude, say if it's cosine or sine, and say the angular frequency times t. So what would this graph be?
It's cosine, the amplitude is 10, and the angular frequency is 2.
So put that all together. So this is 10
cosine 2t.
cosine 2t. Okay, what about this one?
5.
Yes.
Would be 5 cosine 2t.
5 cosine 2t. And the last one?
10 cosine t.
10 cosine t. Yeah, so 1t because it's one cycle for 2 pi.